Tick, tick, tick. The clock is counting down, and eventually it'll reach 0. 0 to what exactly? To the moment when everything flips, when planes suddenly start falling out of the sky, when you can't even buy a bread roll with your card because Visa and MasterCard servers have crashed. And you can't really pay with cash either, because the tax office systems are down too. That is, of course, if anyone's still willing to accept the paper money of a state that's just ceased to exist because the year 2000 has just begun. That's exactly how I'd describe, or rather exaggerate, the panic that built up as we approached the new millennium, all because of what was known as the year 2K bug. In America, where there weren't any major problems yet, those would come exactly 1 year, 9 months and 11 days later, people were genuinely terrified that the entire world would grind to a halt, all because of a stupid glitch in the internal clocks of countless computers. Those same computers that coordinated critical systems we all depend on every single day. The computers you couldn't see, but that quietly kept the world in order. Maybe not as much as they do now, but still, by the year 2000, many key industries were already relying on machines that were about to lose their minds. Enjoy the video. To start, we need to deeply understand how time works in computers and how it's exactly calculated. Every system has its own unique way of keeping time, a specific starting point or epoch from which it counts time in a certain unit, usually seconds. And no matter how advanced technology becomes, every system also has its own inevitable endpoint, the moment when that internal clock runs out of numbers to count. Most problems with this exact setup appear when the clock starts getting dangerously close to that end. Modern systems have their end date set so far in the future that the collapse of human civilization will probably happen first, but early computers weren't so lucky. Back then, limited memory capacity and short-sighted programming choices meant that many early systems simply didn't have enough room or foresight to keep counting time properly forever. A computer doesn't perceive dates the way humans do. For computer, time is just a number, a constantly increasing counter. That number is usually stored in bits, the smallest units of information, zeros and ones. The more bits a system allocates for timekeeping, the wider the range of dates it can represent. For example, 8 bits can store only 256 values, 16 bits about 65,000 values, 32 bits over 4 billion of them, and 64 bits numbers so huge they could represent hundreds of billions of years. However, if part of those bits is used to store the sign of the number, whether it's positive or negative, or if the system measures time in smaller units like milliseconds or nanoseconds, then the actual date range changes. But the core principle remains the same. The more bits you have, the further into the future and the past your computer can count time. Today, the vast majority of systems record time using 64 bits, which means the running out of space problem has been postponed to basically never. But back in the day, it wasn't so obvious. What's interesting is that every computer system also has its own epoch, a 0 point in time, the moment from which it begins counting seconds, milliseconds or other units. These starting points are arbitrary and vary widely between systems. For example, systems based on the Unix kernel, such as Linux, macOS, iOS and Android, count time in seconds since January 1st, 1970. It's known as the Unix epoch. Windows, on the other hand, measures time in ticks, each representing 100 nanoseconds, counted all the way from January 1st from the year 1601. There are many reasons for these choices: historical, technical, and sometimes it's just about convenience. Computers running Unix measure time starting from January 1st, 1970 at midnight UTC, the moment known as the Unix epoch. That's because Unix itself was essentially born around that time. The engineers at Bell Labs needed a simple way to measure time in their programs. Instead of dealing with messy combinations of dates, months, and years, they decided one number was enough: the number of seconds that had passed since a fixed point in the past, that point being the start of 1970. From that moment on, all Unix-based systems and later Linux, macOS, Android and practically the entire internet have been counting time that same way. In Windows, the much earlier starting date comes from technical and business reasons. Windows inherited its timekeeping method from the VMS operating system created by Digital Equipment Corporation, DEC, or more precisely from the engineers who built it. In the 1980s, Microsoft hired hired several top-deck engineers, including David Cutler, the chief architect of VMS. Along with them came many of VMS's unique but practical design choices, including how it measured time. In VMS, the epoch begins on January 1st, 1601. Why that date? Because it's the first year of a 400-year cycle in the Gregorian calendar. This calendar, introduced by Pope Gregory XIII in 1582, has pretty complex leap year rules that repeat every 400 years. In short, years divisible by 4 are leap years, except those divisible by 100, unless they're also divisible by 400. This correlation keeps the calendar in better sync with Earth's orbit around the Sun. That choice of epoch has survived in Windows to this day, one of many little historical quirks kept alive for backward compatibility, ensuring that even programs written in the 1990s can still run smoothly on modern Windows 11. Of course, there were many other systems along the way, now obsolete or highly niche, each with its own unique starting date and sometimes even widely different time units. As for the end dates, that depends on the system and how it counts time, and that's exactly what we'll explore next, because that's where things get really interesting. When a system's counter reaches its limit, it can no longer record the next day. That's when an overflow happens. The counter wraps around back to the start, and that's when all sorts of weird bugs, critical failures, and even complete system crashes can occur. By the late 1990s, most of the world was living under one headline: Year 2K. The arrival of the new millennium meant opportunity and hope for some, but for others it meant a looming disaster. The year 2000 problem. At first glance it sounded trivial, but at its core it was a problem that could potentially paralyze everything, from banks and hospitals to airplanes and even nuclear power plants. Back in the era of massive mainframes, the 1960s and 1970s, computer memory was incredibly expensive. Programmers trying to save every possible byte stored years using only 2 digits. Instead of 1975, just type 75. And it worked perfectly fine, until the clock was about to roll from 99 to 00. On New Year's Eve 1999, countless computer systems around the world could believe that we weren't moving forward into a new millennium, but rather back to the year 1900. And what would that actually mean? For banking systems, loans and deposits might suddenly appear to be 100 years overdue. For airlines, tickets from the future would be considered invalid because the year 2000 would seem earlier than 1999. For industrial systems, time-synchronized sensors and schedules would simply stop working. Governments and citizens alike began to panic. Newspapers warned of a coming digital apocalypse. TV showed people stockpiling candles, bottled water, and food, unsure whether electricity would still be flowing when the clock struck midnight on January 1st, 2000. But then something absolutely incredible happened. The world didn't collapse. Between 1997 and 1999, millions of programmers around the globe worked tirelessly, rewriting code, patching systems, and testing software line by line. It became one of the largest global projects in computing history, costing over 300 billion, and for the most part, it worked. When midnight came, planes didn't fall from the sky, banks didn't crash, and the lights stayed on. Some people still claim the year 2K bug was overblown, but the truth is, it's really easy to say that in hindsight. The reason this disaster was avoided was precisely because of that massive, coordinated effort to fix every potential flaw before it happened. It was the first great lesson in how seriously we should treat the limitations of time in computers. Because if one small decision, like starting the year with just 2 digits, once had the potential to threaten the entire world, what will happen when the next countdown reaches 0? But year 2K was just one of many such issues. And there have been and will continue to be many more of them. Some minor, others potentially catastrophic. While researching this video, I learned that timekeeping in modern computers is an incredibly tricky topic. So here are a couple of examples of time-related problems, both from the past and those still waiting for us in the future. In 1975, a very specific class of mainframe computers, the DEC PDP-10, running the TOPS 10 operating system, reached the end of their internal clock's lifespan. These were massive cabinet-sized machines used by universities, government institutions, and even military organizations. The best modern comparison would be something like a server where multiple users could access one large central computer through separate terminals. The development of the PDP-10 began around 1964, and that's when its internal clock started counting time, until the inevitable overflow, which was set to occur in 1975. Why so soon? As I mentioned earlier, memory was insanely expensive back then, and designing a clock meant to last decades seemed unnecessary in a world where technology evolved faster than anyone could ever imagine. Still, it turned out to be a real problem. Engineers eventually created a fix known as the Date 75 patch, a software update that extended the system's clock range. However, that patch caused new issues since some older programs used the same memory space that was now reserved for the new date field. The fix mostly worked though. The new overflow date was pushed far into the future, February 1st, 2052. Of course, those PDP-10 machines are long gone today, so that clock will almost certainly never reach its new doomsday date. A similar issue affected another line of DEC computers, this time being PDP-8, the first commercially successful mini-computer. By today's standards, it was still enormous, but back then it was truly mini. Even its price, though far from affordable for households, not that anyone had a reason to own one at home in those days, was relatively budget-friendly compared to other machines on the market. That made it a popular choice for hospitals, the military, universities and laboratories alike looking for a smaller, cheaper alternative to massive mainframes. The PDP-8 ran an operating system called OS-8, whose internal clock was set to go haywire in 1978. The cause and the outcome were very similar to the previous case. Engineers had simply allocated too little memory for the time counter. Nothing particularly dramatic, but still another example of how short-term thinking in early computing could lead to long-term headaches. Moving on, the next time-related computer bug appeared on September 18th, 1993, and this one's actually pretty fascinating. It affected games made by Sierra for Apple Macintosh computers. Sierra was a big name back then, responsible for several legendary titles, many of which were built using their proprietary game engine called the Mac Sierra Creative Interpreter, Mac SCI for short. Basically, the Unity or Unreal Engine of its day. Within the Mac SCI engine, there was a function that handled timing and delays in games, things like animation intervals, pauses between character movements, and similar actions. Instead of creating a separate in-game clock, the developers decided to use the Mac's system clock, which measured time in seconds since January 1st, 1904. The engine would take that value and divide it by 12 hours, that's just about 43,200 seconds, to get its own internal time unit. And that's where the bug appeared. On September 18th, 1993, the Motorola 68000 processor, the CPU used in Macintosh computers at the time, started failing to handle the division operation when the result was too large. This dividing operation simply broke mid-calculation, and the game engine didn't check whether the division had succeeded. It just carried on as if everything was fine. The result? The game started misinterpreting delays. What was supposed to be a 1-second pause could suddenly last hours. In effect, many Sierra games became completely unplayable, freezing for absurdly long stretches of time. Sierra quickly released a fix called the Macintosh Date Patch, which restored normal functionality, at least for the moment. But as it turned out, the problem wasn't gone for good. A very similar bug then resurfaced years later in 2007. In 1997, yet another timekeeping glitch struck, this time involving a company that has since long faded into obscurity. Remembered today mostly as a historical footnote, Apollo computers. Their machines run an operating system called Domain OS, which in 1997 suddenly started going haywire. As I mentioned before, most computer systems count time as seconds since a given start date, but Apollo's approach was more complex and far more precise. Their systems measured time from January 1st, 1980, not in seconds, but in microseconds. That's 1/1,000,000th of a second, or this number per unit. This level of precision made Apollo computers stand out in their day, especially for scientific simulations, high-precision calculations, and other advanced applications. Of course, such precision came at a cost. The amount of memory reserved for timekeeping was large for the time, but still finite. And by 1997, the inevitable happened. The counter ran out of space and the clock overflowed. By the time the problem problem surfaced, Apollo computer no longer existed. The company had been acquired by Hewlett-Packard years earlier, so it fell to HP's engineers to clean up the mess. They released special patches that either changed how time was calculated or shifted the epoch forward, effectively buying more time for the aging machines. Because surprisingly, even though Apollo systems were already being phased out, they were still in use in certain niche environments, the kind of specialized setups where replacing an old computer wasn't as easy as just buying a new one. And now yet another particularly interesting case, one that served as a kind of prelude to the year 2K problem, introducing the year 99 bug. As I mentioned earlier, in order to save valuable memory, computers often shortened year values. Instead of storing 1970, they'd just store 70. Therefore, dates were commonly written in the format day-day, month-month, year-year. In programming, there's also a concept known as a magic number, a special placeholder value that tells a program something specific, like -1 for an error, 4 zeros for unknown or missing value, or 4 nines for no data or end of file. So when the calendar hit 9999, September 9th, 1999, some programs and entire systems started to interpret that date very strangely. Some systems froze up, interpreting 9999 as a command meaning end of data. Others deleted or hit records with that date, assuming it was a signal to erase them. Some looped endlessly, producing bizarre and unpredictable results. A few banking and administrative systems even closed accounts or wiped transactions by mistake. It wasn't a global catastrophe on the scale of year 2K, but localized glitches did happen, and some were genuinely weird. Fortunately, as awareness of the year 2K bug grew, engineers also discovered the year 99 issue in time and released patches for many affected systems. Still, plenty of systems were overlooked or left unpatched. On September 9th, 2001, at exactly this time, Unix systems around the world quietly reached a pretty interesting milestone. Their counter-tracking time since the Unix epoch, January 1st, 1970, hit 1 billion seconds. Programmers jokingly dubbed this moment the Unix Billennium, but for some older systems it was no laughing matter. Many programmers didn't store time as an actual numeric value that the computer could calculate with. Instead, they kept it as plain text, a simple 9-digit string 999999999. When the billionth second arrived, there was suddenly no space for the extra digit. It wasn't something the code's creators had ever planned for. Some applications began to malfunction. Others stopped logging events, and a few even rolled their clocks back nearly a century. Luckily, the issue wasn't widespread, and most systems were quickly patched. More modern Unix-based systems handled the Unix Billennium without any trouble, though it served as a gentle reminder that time always runs out eventually. On May 28, 2007, the issue I mentioned earlier, the one involving Sierra Entertainment games on old Macintosh computers, came back to life. The games started freezing again, for exactly the same reason as before, only this time no one could be bothered to fix it. Sierra was practically defunct by then, so it was up to fans of classic Mac games to dig into the old code and release community-made patches that brought those titles back to life. 10 years after the millennial panic, the world got an unexpected sequel, the so-called Year 2K plus 10 bug. The year 2010 started off quietly, until suddenly things all over the world began to glitch out in strange ways. Phones started showing text messages from the future, from the year 2016. In Germany, credit cards stopped working because systems believed their expiration dates were invalid. Even PlayStation 3 consoles freaked out, convinced that 2010 was a leap year and that February 29th existed, even though it didn't. The cause was almost comically simple, a mix-up between two number systems, decimal and hexadecimal. Computers couldn't simply agree whether 10 meant 10 or 16. That tiny misunderstanding was enough to freeze ATMs, confuse calendars, and remind everyone that even the smallest detail in code can ripple across the world. And so every now and then time-related bugs still manage to cause real trouble. Most of them though are relatively harmless or very localized, often caused caused by mix-up of calendar systems or other date formats, like in Japan where they use other calendar system. Another recurring source of problems is the GPS system. GPS has its own way of measuring time. It counts weeks starting from January 6, 1980. Each satellite signal includes the current week number, which increases by 1 every 7 days. But here's the catch. The counter is only 10 bits long, meaning it can hold just 1024 values. So after 1024 weeks, the counter simply reverts back to 0. This happened for the first time in August of 1999 and then again in April of 2019. Older GPS receivers freaked out. Time jumped back to 1980, devices started showing incorrect dates, and some stopped working altogether. Modern receivers now use 13-bit counter, which should last until around the year 2137. Still, older devices running on the original 10-bit protocol will continue to face periodic rollovers. And the next one? Let's see. Right. 2038. Ah, yes, that one. Exactly, 2038. That's the year where GPS receivers will experience yet another rollover, but completely independently of that, something much bigger is also coming. Because here comes year 2K38 problem. Remember when I mentioned Unix systems and how modern 64-bit architectures have effectively pushed their time overflow date into the distant future, basically never? That's true, but that doesn't apply to 32-bit Unix systems where time is still stored in 32 bits, and those machines are pretty vulnerable. On January 19th, 2038, at exactly this time, or perhaps 1 second later, the time counter will overflow. And for every system still counting seconds from January 1st, 1970, that exact counter will wrap back around to 0, effectively resetting time to the beginning of the Unix epoch. When that happens, millions of older devices, routers, security cameras, payment terminals, industrial controllers, anything still using 32-bit timekeeping will suddenly lose track of reality. Even today, some scheduling systems, booking platforms, or calendar tools already start glitching when you try to enter dates beyond 2038. So it's something we need to keep in mind and prepare for. We don't exactly need to prepare for the end of the world, but it's a reminder that we'll need to update or patch every vulnerable system before that date comes. Because time, as it turns out, always catches up, even with computers. So the year 2038 will not be the end of the world. And it certainly is not the end of this video. In 2040, old Macs might roll back to 1904 because their clocks and the HFS file system will stop counting time correctly. In 2042, IBM System 370 mainframes will hit their clock's limits and suddenly jump back in time. In 2048, old SIP planning systems will freeze. Their calendars will simply run out of space for new dates. In 2058, we'll see the fourth GPS rollover as older receivers reset their week counters once again. In 2069, two-digit date systems will confuse 2069 with 1969. In 2079, systems using 16-bit day counters will reset to 0 and some old Nokia phones will stop displaying dates altogether. In 2100, the next leap year bug will arrive, because 2100 isn't a leap year, even though many algorithms will think it is. In 2106, the 32-bit Unix time used in some protocols and file formats will wrap around to 0. In 2108, the classic FAT file system will stop working, taking the zip format down with it. In 2137, and yes, for real this time, even the newer GPS systems will roll over again. In 2262, some programming languages that count time in nanoseconds will break, and by 2464, even Linux most common file system ext4 will finally say enough. And after all of that, the year 4000, when the length of a day will drift enough that we'll need new leap year adjustments, or a year 8000, when it'll happen again, or 10,000, the first year with 5 digits, and eventually even Windows 64-bit time will reach its limit. In the year 30,828, dates will simply cease to exist for those systems. And there are probably many more such dates we don't even know about yet. Bugs that will be discovered and patched as long as the the machines that still use them are still somehow running, until finally, far, far into the future, in the year 292,277,026,596, roughly 20 times the current estimated age of the universe, even the 64-bit Unix time counter will overflow. But that's a date so impossibly distant that by then there will be no computers, no humans, no Earth, no you or your cat, no me, no YouTube. Just the absolute absurd end of all endings. And until that day, somewhere deep within the code, a clock is still ticking, quietly, relentlessly, waiting for its own end of time. Thank you for watching.